Our project is titled B-Ball Brain. My name is Stephen Roberts.
I'm Patrick Sullivan.
I'm Chidubema Rachi.
I'm Mahesh Narayanmurthy.
So the goal of our project is to create a machine learning model that we can use to predict the outcome of an NBA game, as well as find the best substitute if a player gets injured, or find an optimal lineup against an opponent. So our work builds off of the work of these papers and authors. What many of these papers do is attempt to build a machine learning model that only predicts the outcome of a game. We intend to create a more complicated and sophisticated model. So as many people know, basketball is a fairly simple game. There's 5 players on each team, and there's 3 different positions. There's a center, a forward, and a guard.
One of the things about basketball that makes it a little bit more complex is substitutions. So it's not always the same 5 players playing against 5 players. So sometimes players swap, and then there's a new type of new combination of 5 players playing against 5 players. And to measure performance for how well a team is doing or how well these 5 players are doing, we look at the plus minus per minute, which is the difference of their scores for that duration. So if the home team is doing well, they have a positive plus minus per minute, which means that they're winning more points over a span of time than the away team.
So we get our data from stats.nba.com. To train our models, we use about 1,400 games from the 2016 to 17 season. There are about 500 players, and there are about 60 statistics which measure the performance of each player. So we use all of this data in order to train our models. So we split each game into time capsules. A time capsule is the duration of game where no substitution occurs. So each of these bars represents the time at which substitution occurs, and the interval between 2 bars is a time capsule.
So in order to access all of the stats that are available on NBA's website, we created a Node.js script to download the information. It gets all of the season average player statistics, and it also iterates through each game in the season, finds when the substitutions occurs, and then gets the stats between the substitutions.
Once we have downloaded the data using the Node.js API, we use a Python library to load all the data into SQLite database. We then clean up the data, making sure that each of the 5 positions that have to be filled are filled correctly. So the training data that we use has about 29,000 examples from about 1230 games from the 2016 to 17 regular season. The testing data has about 1,900 examples from 79 games from the 16 to 17 playoff games.
As you can see, this is the view from our model. So on the columns we'll have the time capsules, and on the rows we'll have the features of the players. For the consideration, we do the home team first, then start the features of the away team next. So for the rows we have 600 features by 29,000 examples. So in order to predict the actual plus or minus for different player matchups, we implemented regression models to solve this problem. Now as you can see, these are some of the regression models that we implemented. We did cross validation to try and estimate the best parameters for our models. And for the ensemble method, we chose 10 estimators, and found out that more than 10 estimators, the models tend to overfit.
So the results of our regression models are actually in the training data. They perform pretty well, the metrics there. But whenever we looked at the test metrics for it, we saw that our regression models do actually very similar compared to a dummy regressor, which always just predicts the most likely label. So, and some of them actually even do worse.
So we determined that one of the reasons for this poor performance of our regression models is actually due to a lot of noise in our data. One reason that we suspect the noise is that we're taking statistics over these very short 30-second time capsules. So what this means is that there's not much correlation between the features and the plus minus per minute. So one of the ways that we can make our problem a bit better posed is to only look at if a team is winning or losing, which makes it a binary classification problem.
So in implementing the classification models, we chose these models from our scikit-learn library. So we implemented some of the models that we covered in class. And the most interesting the most interesting algorithm that we implemented was the feed-forward neural network, where our hidden layer consisted of 50 neurons. We used a sigmoid activation, and we also implemented dropout. Now, interestingly, you can see this is the result from our classification models. Now, the one thing to notice is, if you remember, during regression, our atomic classifier was doing as well as most of our other models, but here we can see that our atomic classifier, we just outputs the mean of the labels, is about 50% accuracy, while the other models that are doing so well, like logistic regression, Gaussian naive Bayes, gradient boosting, and the feed-forward neural network, are at about 60-something%, which is an improvement from what we had in regression.
So one of the ways this links back to the previous work that others have done is that we can see how well our classifier is actually doing better than the dummy classifier, which of course just outputs the most common label. So in Tor's previous work, their smart classifiers actually increase their accuracy by about 3.5%, whereas with ours actually increases by almost 11%, which is a pretty good indication that our model's learning more than the dumb classifier. So some future work that we could possibly expand on. We only used about 1 season of data, whereas there's at least 20 more that we could have integrated into our training data. And also, testing on the playoff games might skew the test results, since the playoff games are always centered around the best teams with pretty much the best players as well. And also, we might be able to adjust the time capsule length, the minimum duration for that, so then we could maybe even have more data, but we also know that this might introduce more noise into our data.